Chapter 8, Introduction to Hypothesis Testing. Before we begin with Chapter 8, I want to remind you again that with Chapters 5, 6, 7, and 8, remember that's Part 2 of the textbook, we cover issues that lay the foundation of inferential statistics. Compare that to Chapter 1 through 4, where we only talked about descriptive statistics. So in this chapter now, we use the techniques and the concepts that we learned in the last 3 chapters. So we're going to use the Z-scores, the idea of probabilities, and the distribution of sample means to create a new technique called hypothesis testing, which is one of the most commonly used inferential procedures. So in this chapter, really nicely, you can see how everything comes together. After this chapter, you'll be able to understand the logic of hypothesis testing. So again, why are we even doing this? Be able to state hypotheses and locate critical regions, very similar to the things we've done before. Then conduct a z-test and make decisions. Define and differentiate a type 1 and type 2 error. And understand the effect size and compute Cohen's d. And also make directional hypotheses and conduct one-tailed tests. We already talked about the logic of hypothesis a few times. So by definition, a hypothesis test is just a statistical method that uses sample data to evaluate the validity of a hypothesis about a population parameter. In the general hypothesis testing situation, we take a random sample from the population. So let's say we have 10,000 people who have headaches. That's our population. Then we do something to them, right? A treatment. So in this case, we want to try to cure the headaches. We give them a pill. And then individuals in a sample are measured to see if they still have a headache, let's say an hour later, right? If the sample mean is noticeably different from the original population mean, then we have evidence that the treatment had an effect. In this case, this pill actually helps to cure headaches. There is a certain logic to hypothesis tests, and I call them the steps, right? So there is a process. So you always begin by stating the hypothesis about a population. Then you predict the expected characteristics of the sample based on the hypothesis, right? So what do I expect to find? Obtain a random sample from the population. And then you compare the obtained sample data with the predictions that you made from the hypothesis. And if it is consistent, you can say, yeah, my hypothesis is reasonable. If there's a discrepancy, then the hypothesis is rejected. So let me give you an example. So let's assume that based on my observations at 4-year universities, my hypothesis is that male professors earn higher salaries than female professors. So my 2 variables that I can measure here is gender and income. So my population is all professors at 4-year universities. And I predict that when we take a random sample of professors, we will find there's a higher income for males. So I go out, I take a random sample, and then I compare the results from my sample to the hypothesis. If it is consistent, then my hypothesis is reasonable. If my data suggests otherwise, so maybe there is no difference or females actually earn more, then my hypothesis would be rejected. So I can narrow this down even further. There are literally only 4 steps in hypothesis testing. Step 1 is you state your hypotheses. Step 2 is you set the criteria for a decision. Step 3, you collect data and compute your sample statistics. And step 4 is you make a decision based on what you found. And we are going to go over each of those step by step. So step 1 is to state our hypotheses. And you can see, so far we always just talked about singular hypothesis, only one. But now you can see it's thesis, right? So it's hypothesis. That means we refer to more than one. Why is that? So first off, that's the one we've been talking about the whole time, which is now called the alternative hypothesis, or H1. You're also going to see it as HR, the research hypothesis. And that one states that there is a change, there is a difference, or there is a relationship in the general population. So this is the hypothesis we've been talking about the whole time. So if we say female professors earn less money, than male professors, then we are saying there's a difference between, the genders, right? If we're saying your education level is going to influence how much income you have, we talked about that hypothesis a few times, right? Then we are saying there's a difference between, what kind of education level you have and how much money you make. And that is, again, what we refer to as, the book refers to as the alternative hypothesis, and a lot of times you're going to see that I'm using HR for research hypothesis. That's more common. But I said there are two. So this is really the important new thing we are learning for hypothesis, and that is we also have a null hypothesis. A null hypothesis always states that no, there is no change, there is no difference, there is no relationship in the general population. So the null hypothesis would just be there is no difference in salary between female and male professors, or there is no difference in income between the different educational levels. The null hypothesis is always there is no difference, there is no change, there is no relationship. And I don't want to say it's the opposite of the alternative hypothesis, but you're basically just saying whatever you stated in your research hypothesis, no, it's not. There's no relationship, there is no change, there is no difference. But how do we know when we have our results that the data is actually high or low enough that we can say, yeah, our hypothesis is supported? How different do our findings have to be that we can say, yes, this difference in salary is actually high enough that we can reject our null hypothesis? And this is the important part for why we even stating the null hypothesis. Because when we are testing, so anytime we're using a formula for anything that's coming up now, so we are testing, we are always testing the null hypothesis. The research hypothesis is something that we state, but what we are testing is the null hypothesis. Because if you think about it, when we can say, no, the null hypothesis has to be rejected because we found there is a change, or there is a difference, or there is a relationship, then we automatically supported our research hypothesis. So, but again, how do we know that it's actually big enough, the difference, if we found a difference? And this is where the alpha level and the concept of the critical region comes in. And that's where you're going to really see the connection to the previous chapters. In step 2, we're setting the decision criteria. So after we state our null hypothesis and our research hypothesis, we need to set the decision criteria of what kind of sample data would be reasonable if our null hypothesis is true, and what kind of sample data would be very unlikely. The term very unlikely is defined by the alpha level for the test. So the alpha level, or the significance level, is a probability value used to define very unlikely outcomes. The critical region is the set of sample outcomes that would be very unlikely to occur if the null hypothesis is true. If the research study produces a sample that is in the critical region, we can conclude that the sample data are not consistent with the null hypothesis, and therefore we reject the null hypothesis. So the boundaries of the critical region or regions are determined by the probability that's set by the alpha level. So our sample has to produce data to a specific significance level that we're going to call the alpha level that we determined beforehand, to which we compare what our sample data shows. We have to see if our results are within a critical region, falling within the extremes that are very unlikely. And the boundaries of these critical regions are determined by the probability set by the alpha level. So let me show you what this looks like. Because again, a visual is really going to help you. The set of potential samples is divided into those that are likely to be obtained and those that are very unlikely to be obtained, if the null hypothesis is true. So if the null hypothesis is true, again, that means there is no difference in the salaries for females and male professors, then we would expect our sample mean to be in the middle part of the distribution. However, if our sample data mean lies to the right or the left, right? So again, those are the tails and the extremes we talked about before. then there is a low probability that our null hypothesis is true and that there is actually a difference in salary. And you can see this is obviously a generic picture of what the critical regions, and again, that's what we're referring to when we talk about what we talked about before, the tails and the extremes on the outside. Those are the critical regions. And we obviously need numbers so we can compare our data to specific numbers to see if the null hypothesis is true or can be rejected. So again, just like before, kind of get the idea already that this is going to be a C-score that we determined right here and right here. And then we know, oh, past that, towards the tails, right, we're going to find the extreme low probability values that the null hypothesis is true. And we already know from previous chapter that we can determine this by the probabilities from the table and from the C-scores. So the boundaries are referred to as the critical region, and we are setting these boundaries by setting the level of significance or the alpha level for each specific hypothesis test. So alpha defines the critical area, the area in the tails. And we are usually working with an alpha of 0.05, 0.01, or 0.001. And I'm going to show you in detail the differences between each of these. So again, imagine the normal distribution. An alpha of 0.05 means that we have a 5% in the tail. Because remember again that the entire distribution is 100%. We have two tails, and an alpha of 0.05, meaning 5% are in the tails. That means we have 95% inside and 5% in the tails. Since we have two tails, that means we have to have a percentage of 2.5% in each of the tails. Because again, remember, this whole thing is 100%. So 95% is in the middle and 2.5% is on the outside because we have two tails, and those 2.5 plus 2.5 then is the 5%. And this 5% is what an alpha of 0.05 tells you. Because remember again, this is the proportion, this is the percentage, right? This is what we learned in chapter 2. Since we know this is 2.5% for an alpha of 0.05 for a two-tailed test, that means that we have an area of 0.025 in each of the tails, right? Again, that's the same thing. 2.5% divided by 100, this is how you get this area. Well, now we just go back to our table, just like we learned in class. What area in the tail goes with this Z-score? So just go backwards again, find this area in the tail, and you will see that in the tails for 0.025, you read a Z-score of 1.96 right here, and 1, because it's below the mean, of negative 1.96 right here. So since this is always the same for an alpha of 0.05, we know that an alpha of 0.05 has a Z-score of negative and positive 1.96. The boundaries for an alpha of 0.05 are the Z-scores of negative and positive 1.96. Again, let me show you the logic for the next alpha level. Remember again, alpha defines the critical area, the area in the tail or tails if we have talking about both tails. Because later there will be a distinction, but right now we have two tails. We want to find the boundaries for both tails. So normal distribution, let's say now we're setting our alpha to 0.01. That means logically exactly the same thing we just talked about for an alpha of 0.05. That means now we have 1% in the tails. Since we have two tails, that means we have 0.5% in each of them. Because now we know we have 99% in the middle. And you can see, so now the middle got larger and the tails, the areas in the tails got smaller. Well, if it's 0.5%, then we know this is an area of 0.005. Again, you just divide the percent by 100. Same logic, you go to the table and you find this area in the tails. And you will see that this corresponds to a Z-score of negative and positive 2.58. So the critical areas for an alpha of 0.01 is positive and negative Z-score of 2.58. The smaller we set our alpha, the larger the inside gets, the smaller the critical areas get, because again, the alpha defines the critical area. So now lastly, let's use our smallest alpha of 0.001, which means we have 0.1% in the tails. Again, we have two tails, so now that means we have 99.9% in the bulk right here. So that means our tail got even smaller, right? So now we have 0.05% in each of the tails. Now this is an area of 0.0005. Again, just divided this by 100. And if you look at the table again, you can see that this now corresponds to z-scores of negative and positive 3.30. So every time we're talking about an alpha of 0.001, we have a two-tail test, we know we need to use the z-score of negative and positive 3.30, because that means the critical area is now set to a proportion of 0.0005. And what again do we use the critical area for? If our calculated z-score for our sample data is in the critical region, so meaning it's in either one of those two tails, we know we can reject the null hypothesis, which stated that there is no difference, that there is no relationship, which in turn means we actually supported our research hypothesis. So let's do a short learning check. Let's assume a sports coach is investigating the impact of a new training method. In words, what would the null hypothesis say? So please press pause. Let's do another learning check. Is it true or false? If the alpha level is decreased, the size of the critical region decreases. So please press pause. That is true, because the alpha is the proportion of the area in the critical region, right? The critical region, again, is the extremes on both sides. And if we decrease the alpha level, the size of the critical region also decreases. True or false? The critical region defines unlikely values if the null hypothesis is true. So please press pause. This is also true because the critical region is the extreme on both sides, right? It holds the values that are unlikely that the null hypothesis is true. So then our next step is to collect the data. So again, remember step 1, state the hypothesis. Step 2, set the criteria for decision. So setting the alpha level in the critical region. And then step 3, collecting the data so we can actually do the calculations. So the data always has to be collected after the hypothesis is stated. The data always has to be collected after establishing the decision criteria. So step 1 and 2 have to come first. And this sequence is there because it assures objectivity. So I'm sure you noticed up to this point we haven't done any math yet, right? So this is really where everything is happening. In step 3, after we went out and collected our data, we actually compute the sample statistic. And let's say we find a difference, right? But how do we know that the difference between the sample mean and the population mean didn't happen by chance, right? Sampling error. Or the goal for the hypothesis test is to rule out chance as a plausible explanation for the mean difference. And to accomplish this, we first calculate how much difference is reasonable to expect between the sample mean and the population mean, if there is no treatment effect, the standard error. Then we compare the actual obtained difference with this value, and the z-score statistic makes this comparison for us. So we compute a sample statistic, a z-score, to show the exact position of the sample. So in words, z is the difference between the observed sample mean and the hypothesized population mean, divided by the standard error of the mean. A large value for the z-statistic, as defined by the critical region, means that we can conclude that the obtained mean difference is more than can be explained by just simple chance. And then our last step is to make a decision. based on the calculation that we just did in step 3. So if our sample statistic C is located in the critical region, the null hypothesis is rejected. If the sample statistic C is not located in the critical region, so it's in the bulk, right, the researcher fails to reject the null hypothesis. So we're actually not talking about, oh, it's not true or it's true. We either reject a null hypothesis or we fail to reject a null hypothesis. And you can note again that we never really talk about our research hypothesis. Everything is worded in terms of the null hypothesis. If it is located in the critical region, the null hypothesis is rejected. If it is not located in the critical region, the researcher fails to reject the null hypothesis. Next, let's talk about the two types of errors that we can make when it comes to research hypotheses. Sometimes a researcher rejects a null hypothesis that is actually true. So here, the researcher concludes that a treatment has an effect when it actually had no effect. In this case, the researcher falsely concludes that the treatment has an effect, which is then a type 1 error. The alpha level is the probability that a test will lead to a type 1 error. Think of it in terms of a medical test. A type 1 error is where the person doesn't have a disease, but the test says they do. So that's a false positive. It is also possible that the treated sample does not appear to be noticeably different from the original population, even though the treatment did actually have an effect. So in this case, the researcher falsely concludes that the treatment does not have a significant effect, and that is what we call a type 2 error. So the researcher fails to reject the null hypothesis when the researcher really should have, because the treatment actually had an effect. Again, in medical terms, see it like this. A type 2 error is where the person has a disease, but the test doesn't pick it up. So it's a false negative. Unfortunately, a type 2 error probability is not that easy to identify. And now again, I want to give you one example step by step. So let's assume we want to know if it is possible to affect math skills by listening to classical music. I'm sure you heard that before, that when you study and you listen to classical music, then it does something to your brain, and we want to see if this actually affects our math skills. So let's assume we know that for the general population, the math skills form a normal distribution with a mean of 80 and a standard deviation of 20. So what we want to do is we want to take a random sample of students who listen to classical music while studying to get the mean of their math skills. So that's for our sample. If the mean for the sample is noticeably different from the mean for the general population, then we can conclude that listening to classical music seems to have an effect on mathematical skills. However, if the sample mean is around 80, because that's the one for the general population, right, then listening to classical music doesn't seem to have an effect. So that's the big logic for this problem. So again, all we need to take out of this right now is we know that for the general population, math skills form a normal distribution with a population mean of 80 and a population standard deviation of 20. We want to take a random sample of students and then want to see how different the mean of their math skills is. So don't get overwhelmed by this problem. Remember, there are just 4 steps. So let's go through the steps one by one. Step 1, we said, is state the hypotheses. So we are supposed to state the null hypothesis and the research hypothesis. So our research hypothesis, again, the book calls this HA for alternative hypothesis, is just that we believe listening to classical music affect math skills. That's what we think, right? That listening to classical music is going to affect math skills, which would mean that the mean for the population listening to music should not be 80, because we said the general population has a mean of 80. So if there is an effect on math skills, then it should not be 80. And then we have to do the null hypothesis, the one that says there is no difference, right? There is no effect. And that's just saying listening to classical music does not affect math skills. So then we would expect that the mean for the population who listen to classical music will be 80 because it will mean nothing has changed, right? Which means classical music does not have an effect on math skills. That's step 1. The next step we said was locate the critical region by selecting the alpha level. So we know, again, get a visual of it. It really helps for these problems. We know the population mean is 80. And let's assume we want to set the alpha to 0.05. So by default, it's usually 0.05. So unless it's otherwise specified, an alpha level of 0.01 or 0.001, you can always assume it's 0.05 if it doesn't say anything. So by default, SPSS programs, for example, always use an alpha level of 0.05. So we are looking for a different value than the mean of 80. And again, want to know, but how different is different enough that we can actually reject the null hypothesis? So let's say we say setting an alpha of 0.05. We already saw this in a previous slide. This means it's a two-tailed, right? We have upper tail and lower tail. And that means this is 0.0250 of an area in each of the tails. And we said for this one, the C-score is negative and positive 1.96. So this is locating the critical region by selecting the alpha level, 0.05, and then setting our boundaries. So to see if something is different enough, right, we want it to be in the critical region, either here or over here. So if our sample mean is over here, that means, wow, those people did a lot better by listening to classical music. If it would be over here, that would actually be a bad thing because it would be lower than the general population. That would mean, well, it does affect your math skills, but they scored a lot lower, right? But in both instances, here and here, we can reject the null hypothesis. If our C-score that we're going to calculate from our sample that we're getting is in here, then we have to fail to reject the null hypothesis. And as you saw again, up to this point, I haven't done any math yet. It was all setting it up, stating the hypothesis, setting the critical regions, and now in step 3 is where I would go out, collect the data from my sample, and then do the actual calculation. Let's assume that we have a sample of 25 students that listen to classical music, and we find out that the mean score in their math test after they listen to classical music is 89. So we already can see that the 89 is higher than the population of 80, right? But is it different enough that we can say, yeah, this actually works? This is what we're trying to find out. And we do that just simply with our C-score formula. We know the population mean is 80, the standard deviation is 20. We know that for this formula, right, we are comparing the sample mean minus the population mean over the standard error of the mean. And we know for this one, we just have to do an additional formula because that is the standard deviation over the square root of n. But you can see it's really not that different from anything we've done before because at this point, it's just plugging in. That's 20 divided by the square root of 25. So we get a standard error of the mean of 4. Plug this back in here. We know the sample mean was 89, population mean was 80, so we get a C-score of 2.25. And this is the important part now, because I know we've done all of this before. But now we want to see where is so this is for our sample mean, right? We get a C-score of 2.25. So where is that located? And if you look at that, it's located past our C-score that we set in step 2, the critical region of 1.96. So it is in the critical region. Because we can see that means the probability for, and you don't really have to do this, but this is kind of a double check. You already know that this is larger than 1.96. But now we see that this is the probability in here. When you look for a C-score of 2.25, you see that this proportion, this area, is 0.0122, and that's clearly smaller than our alpha level of 0.05. And in the last step, in step 4, we make a probability-based decision about the null hypothesis. We found that our mean of 89 was located in the critical region, so we reject the null hypothesis. The probability that the null hypothesis is true is less than 0.05. So this is how it is reported if we found it to be in the critical region. If we find it not to be in the critical region, then we would show it like this. So we're reporting the p-value of our t-statistic. The probability of obtaining a mean in the critical area is either less than 0.05, that means we reject the null hypothesis, or it is larger than 0.05, and that means there was not enough evidence to reject the null hypothesis. Statistically significant versus statistically not significant. And here you can see a visual of this. So the probability is larger than alpha, means we fail to reject the null hypothesis, and if we find our probability to be smaller than alpha, then we reject the null hypothesis. There are certain assumptions for hypothesis testing with z-scores. The first one is that we have to do random sampling. So our data has to come from random sampling. And then also, it has to be independent observation, meaning that each observation or measurement is not influenced by any other observation or measurement. So that's kind of the logic of tossing a coin, right? So each time you toss a coin, there's a 50-50 chance of either heads or tails. So each toss is independent of the toss that came before. So it doesn't matter if we had 50 tails in a row already. That doesn't mean that our probability got larger to actually get a head on the next one, right? It's still going to be a 50-50 chance. The value of the standard deviation is not changed by the treatment. And then also that we have to have a normally distributed sampling distribution. There are various factors that influence the outcome of a hypothesis test. So if the z-score is large enough to be in the critical region, we said then we reject the null hypothesis and conclude that there is a significant treatment effect. And otherwise, we said we fail to reject and conclude that the treatment does not have a significant effect. And the most obvious factor influencing the size of the z-score, if you just look at the formula, is if there's a huge discrepancy between the population mean, so that's the mean that didn't get the treatment, right? And then your sample mean, right? So if there's a huge difference between the two, then that's an indication that the treatment sample is obviously noticeably different from the untreated population and usually supports a conclusion that the treatment effect is actually significant, because this is huge difference between here is going to lead to a large Z. And then it's more likely to be pushed to the tails, because we know it's going from 0 in the middle to, again, all the way, 3 and everything outside. Another factor that influences the outcome of a hypothesis test is the variability of the scores. The more variability there is, the larger the standard error is. So let me show you this in an example. So let's assume we have a population mean of 80 with a standard deviation of 20. And for our sample, we know we had 25 people in our sample with a mean of 89. So for this example, we would get a z-score of 2.25. Let's assume everything stays the same, but now we just increase the variability, right? So this stays the same, but now our standard deviation for the population is actually 30 instead of 20. So doing the math exactly the same way, but just now with the standard deviation of 30, you can see that we get a z-score of 1.50. More variability, larger standard error, right? It went from 4 to 6 because the standard deviation went from 20 to 30. Since this is the denominator, this means we're now coming up with a smaller z-score. Well, this one is larger, so it's more likely to be pushed out into the tails, which means it's more likely to be actually statistically significant than this one right here. More variability, larger standard error, less likely to be statistically significant. Another factor that influences the outcome of a hypothesis test is the number of scores in the sample. And we already talked about the law of large numbers before. The larger the number of people, the smaller the standard error. So if we look at the example again that we used in the previous one, let's assume we have standard deviation of 20, population mean of 80, 25 people, and 89. We said we come up with a z-score of 2.25. So what if we increase only the number of people? So everything stays the same, but now instead of 25 people, we have 100 people, right? Doing the math over again, because now we are taking the the standard error of the mean in the denominator has the square root of n, this is how this is influenced, right? So this is a lot larger now, which means that we come up with a standard error of 2, right? Because so smaller standard error, if we increase the number of people, and therefore we end up with a much larger C-score. And again, than this, right? So this one is a lot more likely to be in the tails to be statistically significant than this one right here. So larger number, smaller standard of error, therefore larger C-score. So what we've been talking about the whole time is called the standardized hypothesis testing procedure. And it's also called a two-tailed or non-directional test because the critical regions that we looked at involves both tails to determine if the treatment increases or decreases the target behavior. So that's when we say, yeah, classical music is going to affect math skills. We didn't say it's going to increase the math skills or decrease the math skills. We just said it's going to affect it. So that means we left it open if we're going to find the C-score in the top or in the bottom tail. That's what's called a two-tailed or non-directional test. But a lot of times we don't just want to say something, about that something is something affecting, right? But we want to predict a direction. So for example, we predict that listening to classical music might actually increase the mathematical skills in student, right? That's a direction. We think we're going to find it on the upper side, right? Hopefully that would mean that the treatment had an effect, right? Usually a researcher begins an experiment with a specific prediction about the direction of the treatment effect. And that is what's called a directional or one-tailed hypothesis test. So when a specific direction of the treatment effect can be predicted, it can be incorporated into the hypothesis. So we just have to be careful with the wording. So in a directional or one-tailed hypothesis test, the researcher just specifies either an increase or a decrease in the population mean as a consequence of the treatment. The logic for setting the critical region for a directional or one-tailed test is exactly the same as I explained to you earlier. But the one-tailed test allows rejecting the null hypothesis with relatively small difference, provided the difference is in the predicted direction. Instead of just having that area that our alpha level determines, having that split up in two tails, that area is now in just one tail. So let's assume for this one, we're setting an alpha of 0.05, right? And we just saying math skills are going to increase because people listening to classical music. Then we expect it to be up here. Down here would mean decrease, but we're only doing a one directional test. If our C-score is in this critical region right here, we can reject the null hypothesis because the data indicates that the null hypothesis is wrong, right? Again, I don't like using that word, but that it's statistically significant. In here, it's not statistically significant. If we have an alpha of 0.05 in here, that just means that we have 0.0500, right, in the area right here. And we do the same thing as before. If this is the area in the tail, that refers to a C-score, and you get that from the table, of 1.65. So you just got to be careful when it's a one-tailed test. The C-scores are not the same that we talked about earlier because we're now not splitting up the region, but it's actually only in one of the tails. A hypothesis test determines whether the mean difference obtained in a research study is greater than is expected simply by chance, right? By sampling error. We talked about that. And we said the standard error is used to determine how much difference is reasonable to expect. However, in some cases, especially with large samples, the standard error can be very small. And in these cases, a tiny mean difference may be enough to be statistically significant. So concluding that the treatment effect is significant doesn't really tell us anything about the actual size of the effect. And it doesn't imply that the effect is large. So therefore, we also need to report on the effect size. Effect size measures the absolute magnitude of a treatment effect, independent of sample size. And this is when Cohen's d comes in. Because with Cohen's d, we measure the effect size. It is computed by just taking the mean difference over the standard deviation. Mean difference meaning the population mean with the treatment minus the population mean with no treatment over the standard deviation. And the magnitude that we then get is, if you get a Cohen's d of 0.2, we say usually it's a small effect, of 0.5 medium effect, and 0.8 large effect. So it can go above 1. It's not like 1 is the top. But just remember it as a Cohen's d of 0.5 is a medium effect. Anything below that, small effect. Anything above that is a large effect. When we talk about the concept of statistical power, the power of a hypothesis test is the probability that the test will reject the null hypothesis when there really is a treatment effect. And as the size of the treatment effect increases, the power of the test also increases. And other factors that increase power are increasing the sample size, increasing an alpha level, and switching from a two-tailed to a one-tailed test. So think about it. Whenever a treatment has an effect, there are only two possible outcomes for a hypothesis test. We can either fail to reject it or reject the null hypothesis. So because there are only two possible outcomes, the probability for the first and the probability for the second must add up to the 1. Because remember, probability always adds up to 1, right? So when we said that when we reject a null hypothesis that is actually true, we conclude that the treatment had an effect when it actually had no effect, we made a type 1 error. And when we failed to reject the null hypothesis, but there was an effect, we accepted it as true, but there was an effect in the treatment, we made a type 2 error. And in this case, the probability is what's called beta. So the probability must have an outcome of p equals 1 minus beta. And the power of a hypothesis test is equal to 1 minus beta. Again, it sounds very complicated, but if the power of the test is 70%, then the probability of a type 2 error is 30%, right? Because it is a 1 minus 0.7, and that's a 30%. So to calculate power, however, it is first necessary to make assumptions about a variety of factors that influence the outcome of a hypothesis test. So looking at the influences on power, as effect size increases, power also increases. Larger sample size produces greater power. And using a one-tailed test, a directional test, increases the power compared to a two-tailed test. And decreased power is kind of the opposite, right? Reducing the alpha level, making the test more stringent, reduces power. And also using a two-tailed non-directional test decreases power, again, relative to a one-tailed test. Additional practice problems are posted in our module for this chapter in Canvas. Please remember, if you need help at any point, just send me a short email and I'm happy to help you.